Good morning, ladies and gentlemen. I am Lieutenant Junior Grade Karagiannopoulos Faethon, and I'm going to present you power plant-related measures for improving energy efficiency in ships. The drivers which have led to an increased popularity of energy-saving policies in the maritime sector are mostly the regulations imposed by various environmental agencies and the financial crisis with the until recently increasing price of the bunker oil. The results of these energy efficiency policies are, first of all, the cost savings, the cost savings and the environmental benefits. In the first case, ship owners and operators benefit, while in the latter, the benefits involve the whole society. The first protocol that set the rules for the regulations was set in 1997, the Tier 1, and this one was also revised by the Annex 5 of MARPOL 7378 in 2008. This Annex 5 protocol defined two sets of requirements. The first requirement is the global requirements, Tier 2, and the second one is the Tier 3, that's only applicable to ships in emission control areas. Except from the NOx regulations, Annex 5 also defines regulations for the SOx emissions too, as can be seen on the photo. The emission control areas, the existing emission control areas, are the ones shown on the map till now, and maybe there will be more in the future. However, the sets of these regulations presented in the previous slides increase the complexity of the new engines. In the current state of technology, the fuel efficiency of low-speed diesel engines is around 55%, while this number is a little bit lower for medium-speed diesel engines by 3 to 4%. In the following paragraphs, we are going to present you some of the most practical energy efficiency measures that can be applied to engines and also lead to, at the same time, comply with the IMO regulations. The first method that we present you is the low-speed diesel engines with a longer stroke-to-bore ratio. Super long-stroke engines offer a variety of advantages. First of all, they have an increased swept volume that leads to a larger mass of air and fuel that can be taken inside the cylinder, and as a consequence, this fact leads to a higher power output. Furthermore, the increased piston regression all increases the combustion time during the stroke, leading to an improved fuel burning. Another significant advantage is related to the propeller coupled with the engine. The longer the stroke, the lower the RPM of the engine. Low RPM allows for the use of a propeller of a larger diameter and considering, of course, the geometry of the vessel. A propeller of larger diameter has a better efficiency rate, about 4 to 7%. Furthermore, we can also use a lower grade fuel, and of course, we have a much smaller environmental footprint for the same power output. The only, let's say, bad thing about this is the increased maintenance cost, because we have a higher forces on the guides and on the bearings. The next measure that we're going to present is the slide fuel valves. Their advantage is that they don't have a sack volume comparing to the conventional injectors. This sack volume that can be seen on the conventional injectors retains a small amount of fuel after the combustion, and this fuel leaks into the chamber and causes incomplete combustion. The incomplete combustion is the reason for the engine fouling, the smoke formation, and the hydrocarbon and particulate emissions. As a result, by using slide fuel valves, we have a lower fuel consumption, and we also have a better low load performance. We can see here the results, and and the reduction in the consumption. Another measure that we also examine is the electronic control injection, or common rail. With the development of reliable microprocessor and computer controls, we can now control the timing of the fuel injection, the quantity of the fuel, and the exhaust valve timing. Electronic control in low-speed diesel engines results in around 2 to 2.5% SFOC reduction at low and medium load levels. Furthermore, we also have a reduction in NOx emissions. The key to the common rail system is the servo-hydraulic system, which regulates the fuel injection operation. In the next, we can see here the servo-hydraulic system. And in the next slide, we present the reduction in SFOC due to the use of common rail system along the whole range of loads of the engine. Another measure that we also examine is the operation of the engine at low speed loads. This measure leads to reduced fuel consumption. However, we should also take into account that at low levels we have a NOx emission increase. There are three load ranges that an engine can be SFOC optimized: the high load, the partial load, and the low load. You can see the relevant percentages. With the use of partial load engines, we can have a SFOC reduction of around 5 grams per kilowatt hour, and that means a fuel cost reduction of around 3%. The methods that we can tune the engines in order to achieve the partial load engines are the exhaust gas bypass, the most practical methods, let's say, exhaust gas bypass, the variable turbine area or turbine geometry, and the engine control tuning. In all these aforementioned methods, we can see that we have a SFOC reduction, and due to the use of partial load engines. Another method that we are going to examine is the engine derating, a parameter that plays an important role to the function of the engine is the ratio of maximum firing pressure to the mean effective pressure. The higher this ratio, the lower the SFOC. Thus, selecting an engine with a higher maximum continuous rating and then derating it leads to a lower maximum continuous rating. And of course, it also leads to a lower mean effective pressure. So the derated engine operates at lower RPM while yielding the same ship speed. Furthermore, we can also use a larger propeller with the advantages that we mentioned before. Here we have a case study. We present a typical Suezmax tanker, which is originally specified with a 6-cylinder. And here we have the scenario of replacing the 6-cylinder engine with a 7-cylinder engine. And the results, as can be shown on the study, can lead to a daily fuel consumption, to a reduction of daily fuel consumption by 3.4%. Furthermore, depending on the oil prices, we can have a payback time that varies from 3.5 to 6 years, as can be shown on the photo. Furthermore, a different approach that a lot of manufacturers have also used is the use of dual fuel engines. The major engine manufacturers offer two versions of these engines. The first one is the dual fuel engines that use both liquid and gas fuel, and the other option is the gas engines that they simply use LNG. A dual fuel engine is based on a traditional engine which is retrofitted in order to also burn LNG. At low loads, dual fuel engines operate, they just operate on liquid fuel, but in the higher loads, they also use gas for their operation. Plus, they also produce the same power density and torque curve with a linear air-to-fuel ratio. In gas engines, we have the natural gas that is introduced into the intake system before the inlet valves, and the ignition of the engine starts in a pre-chamber where the mixture is rich in gas. A furthermore method that is also used nowadays is the shaft generators. Nowadays, the development of power electronics allows us to have a fixed frequency. Despite in the past, in order to have fixed frequency, we had to use the CPP propellers. But nowadays, with the power electronics, this has become feasible. Another such an example is in the Hellenic Navy, the general support ship HS Prometheus that use shaft generators. It should also be taken into account that there is also a power loss developed by the propulsion engine, which is around 8%. The significant amount of heat generated by the machinery plant can be used to power an exhaust gas turbine, or can also be used for a steam turbine. According, as we can depict it here on the slide, according to the ABS, to the manufacturer, we can have an increase of up to 11% in large low-speed diesel engines. Now we are moving to the alternative fuels. Natural gas is the major alternative to traditional liquid fuels, and we use natural gas in its liquefied form because it has less volume, and it is considered to be the most environmentally friendly fossil fuel, as it totally eliminates the sulfur emissions, as it's sulfur-free, and it also reduces the nitrogen and carbon emissions. Yes, today there are 48 LNG fuel ships with dual fuel engines, and there are another 40 under construction, according to the data that we have nowadays. But to support the increasing number of LNG fuel ships in operation, we should have the appropriate infrastructure, supply infrastructure, that is still inadequate. However, this is a challenge since the bunker suppliers, from the one hand, are unwilling to invest in the required infrastructure until there is sufficient demand, while the ship owners, from their part, are also unwilling to invest in LNG fuel ships until there is adequate supply. The most LNG hazards that stem from the use of LNG are the following. The first one has to do with the cryogenic effects from the LNG, while the second one has to do with fire and explosion. Once the LNG has leaked and starts to evaporate, it turns to its gaseous state from its liquid state. There is a formation of a gas there is a formation of a cloud consisting of methane. This cloud is ignitable, and it can use to an explosion called bleed. Also, there is a technical issue that concerns the use of LNG with the unburned methane emissions that it has. There are some emissions that are mostly they mostly have unburned methane, and this can lead to an explosion. Methanol. Methanol is another fuel for internal combustion engines, which is mostly produced by natural gas and biomass. It is widely available and can be safely transported and distributed using the existing infrastructure. Compared to LNG, its main advantage is the lower cost when retrofitting the engine. At the same time, it can also be stored to the existing hull tanks, while, on the other hand, LNG requires cryogenic storage tanks. Biofuels include a wide range of alternative fuels produced by biomass and bio-waste. They are mostly used as a blend with ordinary marine bunkers in order to comply with the regulations. The most common blend that is used is the fatty acid methyl ester, or FAME, as depicted on the slide. They are sulfur-free, and the nitrogen emissions are slightly higher compared to the conventional fuels. And if we want to examine the CO2 emissions, we should do a careful and detailed assessment in order to examine any case at a different point of view. The only disadvantage about biofuels is the higher cost compared to the conventional marine fuels, and there are also some technical issues referring to the fuel instability and corrosion. Hydrogen. Hydrogen is mainly used as a fuel in the fuel cell systems that convert the chemical energy of a fuel into electrical energy. They have a minimal environmental impact since the product of the combustion is simple water. Although the first marine application were on submarines, there is a growing interest in their commercial use in the marine transportation too. It seems that it will take some time before fuel cells come as a competitive alternative option. The main drawbacks from the use of hydrogen is the high capital cost, the storage of hydrogen, and of course the lack of infrastructure in order to supply coast-to-coast delivery. Before concluding our analysis, we will study the use of the aforementioned methods within a naval fleet, using the Hellenic Navy as a case study. The Hellenic Navy fleet, is quite diversified, as it includes all different kinds of vessels, from fast combatants, like frigates, to slow ships, like mine hunters. As a consequence, there is also a large variety of engines used. This variety includes medium speed diesel engines, fast-speed diesel engines, and also gas turbines. Except for the high cost, but however, the adoption of a common energy policy for all these ships is a difficult task and a complex case. Except from the high cost, there are also some other operational parameters that should also be taken into account, such as the availability of the ship during the installation process, or the impact that can have on the endurance of the ship, or of course the top speed that they can also develop after the installment of the new system. There are a number of measures that can be adopted in order to increase the fuel efficiency of the Hellenic fleet. Such examples can be the electronic injection, the tuning for a specific range of load, or the use of sub-generators. However, alternative fuels, such as LNG, are only recommended for the fuel supply vessels as they need a large fuel storage volume. When it comes to gas turbines, we can replace the existing gas turbines with a reliable and a less fuel-demanding diesel engine. This was successfully done in 2 patrol boats of Asheville class in the past. And there are also other measures. The other alternative that we can have is retaining the gas turbine while at the same time using a waste heat recovery system similar to the Type 45 destroyers of the Royal Navy, British Royal Navy. Finally, an alternative energy source that is currently used by the Navy in its new class submarines, Type 214, is the fuel cell propulsion system. So, to sum up, there is a large number of available options in order to increase the energy efficiency of the propulsion and power generation plant. These options vary from engine modifications to alternative fuels and can be either applied individually or in combination. However, the optimum selection of the system is many times a difficult task, as it depends on a variety of factors, such as the type of the ship, the payload, and the operational profile. As a consequence, prior to selection and installation of any system, it is necessary to conduct a detailed analysis for the assessment of the economic viability and performance of every option. Thank you very much for your attention. We are at your disposal for any questions.
Αναφέρατε ότι το ατμοκάψιμα θα ονομάσουμε αντικειμενικώς. Αναφέρατε λοιπόν ότι you mentioned that biofuels have a disadvantage of corrosion.
Yes.
It's bigger than the corrosion that biofuels provide, is bigger than the conventional fuels provide. And if so, what?
Kind of measure.
Yes, and what is the cause of the bigger
corrosion problems?
There is a corrosion problem. However, we haven't examined what measures we can take so as to eliminate it. If you want, we can answer you in a Wikipedia address.
Let me answer this. I'm also a co-author on the paper. You can either chemically treat the fuel or you can use specific coatings in the tank.
And the corrosion is
due to bacteria that develop in the fuel.
the conventional fuels don't.
They do not have this problem.
Any other questions? The problem with corrosion is not only on the tanks, but it's also on the city. So, what you have to do is have more regular maintenance and cleaning. You have to clean. Another problem is the power density of the fuel. You have no heat bind. So you have to make changes in the pumps. And all you have to lower the power to produce. Maximum continuous rate. Any more questions? I have one question.
At one point you talked about upgrading the ship by changing it from gas to back to diesel.
Yes, correct.
So my question is why? What's the reason that you go back apparently older technology?
Yes, as is the main topic, as the main matter of the presentation, we want to improve the ship energy efficiency. So gas turbines are not so efficient, just like the old diesel systems. As we mentioned before, a low-speed diesel engine can have an efficiency rate of around 55%. But a gas turbine can only reach around 30–35%. So if we change to this system, from the one hand we lose in speed, the maximum speed is not going to be the same like gas turbines, but we will have a reduction in the smoke and in the fuel consumption. That's why I also mentioned the operational profile. What you want to do with this ship? Do you want to have a high speed in order to go quickly into a certain area, or you just want to make a transition? That's why I also mentioned the operational profile of the ship.
And I add something to obviously gas turbines are used for the high speeds. One example we have over there was the accident class of power boats. So when we purchased those boats, they had a 1600 gas turbine. So for us, since it was supposed to be used for battling on loaded speeds, and those speeds for that knots, diesel engine was the best solution. How at the same time, calculations and the speed out we need. Another possible case that we have here is we have done some studies about that, replacing the low power gas turbines that the glass turbines uses, and they will keep the high power gas turbines for high speeds for splitting. But the possible scenario is to replace solid for the delivery of the piston by consulting large motor and cast verifying different depths of pressure. And for example, the newer classifications we have make on 100, they have what we call combined diesel or gas. So we use diesel engines for the economic speeds and slow speeds. For the fuel consumption, we have a lot of high speeds. Very useful. There was a question by the
Yeah, it's rather common. First of all, there are biofuels which are not suffering from bacterial presence. Like
I know you're a professor. Take me a minute to let it. You're a professor, your name?
Christopher from NDUA. So, this is one thing. Second is that there is technology, and we can develop technology in order to provide bacterial-less, corrosion-less let's say, biofuels and this kind of thing by providing either electrical catalysis or magnetic catalysis or combination of them. We have seen results demonstrating a really improved performance of the fuel, of the different kinds of biofuels by using such methodology.
This is actually true. As you mentioned, there is a wide range of biofuels available. So not all of them suffer from exactly the same problems. And there are technologies under development. This is true. It is, we can say, relatively new technology. So there are